Assalamu alaikum. I'm Mehak Irfan and my department is BS Biotechnology. So today my topic is thermoelectricity. Thermoelectricity is the direct conversion of thermal energy into electrical energy, typically through the use of semiconductor materials. And the applications of thermoelectricity are aerospace, refrigeration, pyroelectricity, batteryless radio, and powerful generation. Thermoelectric material work and challenges faced in developing efficient thermoelectric material. Thermoelectric materials are materials that convert thermal energy into electricity due to the temperature difference or thermoelectric effect. The thermoelectric effect occurs when two different materials are brought into contact and a temperature difference created, causing electricity to flow through the junction. This creates a voltage between two materials called Seebeck voltage that can be used to generate electricity. The challenge in developing efficient thermoelectric materials lies in optimizing the material thermal conductivity and electrical conductivity while minimizing lattice thermal conductivity and other related material properties. By optimizing these properties, efficient thermoelectric material can be developed to harvest energy from waste heat and make power generation more efficient and sustainable. So the principle of thermoelectricity is a process in which electricity is generated as a result of interaction between a temperature difference. The principle of thermoelectricity are Seebeck effect, Peltier effect, Thomson effect. Seebeck effect. The Seebeck effect is the phenomena whereby a voltage is created in response to a temperature difference in a junction of two dissimilar materials. This phenomena was discovered by Thomas Seebeck in 1821 and is the basis for thermoelectricity. Peltier effect. Peltier effect is the phenomena whereby a temperature differential is created when a direct electrical current is applied to a junction of two dissimilar materials. This phenomena was discovered by Jean Peltier in 1834 and is related to thermoelectricity. Thomson effect. Thomson effect is the phenomena whereby a change in temperature is created when a direct electric current passes through a material. This phenomena was found by William Thomson in 1851 and is closely associated with thermoelectricity since it deals with the heat absorption or release of material when an electric current passes through it. Factors that influence the thermoelectric performance are Seebeck coefficient, thermal conductivity, and electrical conductivity. Seebeck coefficient. The Seebeck coefficient, also known as thermopower, measures the electrical voltage generated in response to a temperature gradient. In order for a material to generate a sizable voltage output, it needs a high Seebeck coefficient. Thermal conductivity. Thermal conductivity measures the ability of heat to pass through a material. A material efficiency depends on its ability to reject heat, so a thermal conductivity can have a negative effect on thermoelectric performance. Electrical conductivity. Electrical conductivity reflects a material ability to allow current to pass through. Materials with high electrical conductivity will impede the flow of electrons due to excessive electron-electron collision, thereby reducing the overall thermoelectric performance. Material with a high Seebeck coefficient, low thermal conductivity, and low electrical conductivity are the most efficient for the thermoelectric application. To further improve the thermoelectric performance, nano structures, semiconductors material, and advanced doping techniques may be used. So the next topic is types of thermoelectric material. Thermoelectric material can be broadly categorized into three different categories. The first one is inorganic semiconductor, then organic material, and hybrid material. Inorganic semiconductor. These materials are made from a variety of semiconductor elements such as bismuth, telluride, and can effectively convert heat into electrical energy at high temperature levels. They are generally composed of INAS and are typically in the form of bulk or thin film structure. Thermoelectric material. Organic thermoelectric materials are composed of various organic polymers such as polyethylene or polysilene, which can generate as an electrical power under certain temperature. They have a low intrinsic power efficiency, but they still can provide very useful thermoelectric performance for specific application. Hybrid thermoelectric material. Hybrid thermoelectric material integrate organic polymers with traditional inorganic semiconductor materials in order to improve the overall performance. A combination of organic polymers and INAS produce unique hybrid materials that can provide better thermoelectric performance than either material alone. So the advantages and disadvantages of thermoelectric materials are advantages of inorganic semiconductor. It is self-powered operation, low cost production, long operational lifespan. It is environmental friendliness, high thermal energy conversion efficiency. And the disadvantages of inorganic semiconductor are poor thermal conductivity, heavily affected by self-heating, low switching frequency, limited temperature range, and low gain factor due to poor electrical band gap. Advantages and disadvantages of thermoelectric materials are organic thermoelectric materials have low cost and are easily to synthesize, allowing for lower cost production of thermoelectric devices. They are lightweight, making them ideal for use in application where weight is a critical factor. Then organic thermoelectric materials can be engineered to have low environmental impact and to generate electricity from waste heat. So the disadvantages are organic thermoelectric materials generally have low efficiency than inorganic materials, meaning that they require more energy input to generate the same amount of power output. The stability and reliability of organic materials may be lower than their inorganic counterparts. The exact electrical properties of organic materials are difficult to predict, causing some difficulty in screening and optimizing different materials. Advantages, and so the next are advantages and disadvantages of thermoelectric materials. Advantages are thermoelectric materials include higher efficiency than traditional energy conversion methods, ease of fabrication, and scalability for different applications. They can also provide a way to harness otherwise wasted energy from heat sources like solar radiation. Further, they can also be used to create semi-permanent energy sources since they have a long shelf life without significant degradation. Disadvantages. The disadvantage to thermoelectrics are limited by their lower power densities, meaning that they cannot generate great amounts of energy in small areas. Additionally, their use requires complex controls and circuitry to regulate the current and voltage, making them difficult to use without additional equipment. Finally, the materials and production process can be expensive and may require specialized tools. Materials that have been used for thermoelectric application. There are common materials that have been used, and that is bismuth telluride, lead telluride, silicon germanium, silicon filled polymers, transition metal compounds such as antimony, selenide, telluride, and oxides. Design strategies used to optimize the thermoelectric performance of materials. Various design strategies are used to optimize the thermoelectric performance of materials such as doping, band engineering, nanostructuring, photon engineering. Doping. Doping is the process of introducing impurity atoms into a semiconductor material to adjust its electrical properties. This process allows us to modify the electrical conductivity of the material, controlling its thermoelectric performance. Band engineering. Band engineering involves manipulating the energy band gaps that govern electron transport in a material by modifying their electronic structures and doping levels with strategic materials. By doing this, it is possible to tune the conductivity of the material, increasing or decreasing it and thus optimizing its thermoelectric behavior. Nanostructuring. Nanostructuring involves fabricating materials nanostructure the different geometries and nanosecond feature sizes that permits the control of phonon scattering and also the optimization of Seebeck coefficient. Photon engineering. Photon engineering is the study of photon interaction with materials in order to manipulate heat transfer by utilizing selective shadowing or thermal insulation. Photon engineering can be used to attenuate unwanted convection and radiation losses, leading to improved thermoelectric performance. Strategies that are used to improve the thermoelectric performance of specific materials. First one is doping strategies such as modulation doping or two-band doping have been used to improve thermoelectric performance of materials such as bismuth, telluride, and indium antimonide. Band engineering strategies have been used to improve thermoelectric performance of materials such as bismuth telluride, lead telluride, and lead selenide by controlling their band gap structure. Nanostructuring strategies such as doping and charge engineering, reactant, mediated synthesis, electrical modification, and interface engineering have been used to improve the thermoelectric performance of material in several ways. Photon engineering strategies have been used to improve thermoelectric performance of materials such as bismuth telluride, silicon nanowires, graphene, and topological insulators. Current and potential applications of thermoelectric materials. Thermoelectric materials have many current and potential applications, including first one is waste heat recovery, power generation in remote location, cooling in electronic devices. So let's explain waste heat recovery. In waste heat recovery, thermoelectric modules are used to convert the thermal energy produced by a device such as a car engine into electrical energy, which can then be used or stored for future use. Then power generation in remote locations. Power generation in remote location is another application as thermoelectric devices can generate energy from sources such as hot springs and geothermal sources without the need for external sources of energy, such as electricity. Cooling in electronic devices. Thermoelectric materials can be used for cooling in electronic devices because they absorb excessive heat generated by the device and dissipate it to the surrounding environment. Additionally, thermoelectric materials can be incorporated into temperature measurement and control systems, where they can sense and accurately regulate temperatures in mediums such as food refrigerators and reactors. Finally, thermoelectrics can also be used to harvest energy from natural environments such as solar radiation. So there are examples of how thermoelectric materials use in current and potential application. First one is thermoelectric materials have been used in waste heat recovery application in a variety of ways. One example is the use of thermoelectric modules to capture and convert low-grade waste heat from thermal processing into usable electric power. Thermoelectric materials have been used in remote locations to generate power by exploiting the temperature differential between 2 points. For example, a thermoelectric generator can be powered from the temperature differential created by an external heat loss and the ambient atmosphere. Thermoelectric materials have been widely used in cooling digital devices. The materials are known to be extremely energy efficient due to their ability to transfer heat electronically from hot to cold without the need for a traditional cooling system. Next is challenges faced in scaling up the technology. The challenge with scaling up this technology lies primarily in the cost of materials and assembly, as most thermoelectric materials must first be customized to match the specific application requirements. Additionally, due to their high cost, many commercial applications opt to use thermoelectric material for niche application. Finally, while thermoelectric materials are highly efficient, they are limited to lower temperature, which can also limit their effectiveness in some larger scale application. Future direction. The future prospects for thermoelectric materials and the research direction that are currently being pursued are development of new materials, optimization of existing materials, and integration of thermoelectric material into new applications. The development of new materials. Development of new materials has been spurred by the search for high efficiency and low cost thermoelectrics. This has been fueled by advances in synthesis methods such as rapid annealing and hydrothermal synthesis. as well as doping and alloying techniques. As a result, many novel materials such as all these base systems have been created and are being tested for their thermoelectric properties. Optimization of existing materials. Optimizing existing materials is necessary to improve their thermoelectric properties. This can be done through alloying, doping, nanostructuring, increasing carrier concentration, and controlling their concentration profile, band gap engineering, and other techniques. Alloys have been shown to increase the power factor and figure of merit compared to the individual constituents. Integration of thermoelectric material into new application. Integrating thermoelectric materials into new application is another important research direction. For example, combining flexible and mechanical robust thermoelectrics with bilateral graphenes in solar cells has improved energy harvesting efficiency and cycle life. Additionally, nanostructured thermoelectric materials can be used to convert waste heat to useful electricity in a variety of energy conversion systems. At the end conclusion, thermoelectric materials have considerable potential to improve energy and environmental sustainability. By utilizing the conversion of heat into electricity, thermoelectrics allow for greater energy efficiency by eliminating the requirement of a combustible source to produce electricity. This also helps to reduce pollution from burning of fossil fuels as well as reducing the cost to energy production. Then, thermoelectric materials are also helpful in capturing and storing wasted heat, such as from engines or industrial processes. This is then used for a range of energy production applications, such as powering off grid homes or charging devices. Along with greater efficiency, thermoelectric materials have many other advantages in improving sustainability, durability, and the absence of toxic materials or pollutants. Additionally, they can be used to improve air quality through the capture and conversion of harmful emission produced by factories and vehicles. Thank you.